Hello again. Are there any more questions relating to those papers? If not, I would like to show you another method which comes, let's say, from a scientist who has been watching the nature and is quite popular today for optimizing circuits, materials and problems in engineering, and that is called particle swarm optimization. So at the beginning possibly there was a scientist who was watching bees over a meadow, finding nice flowers with sweet water in it, and that gave birth to a method which comes from, let's say, an agent-based part of the artificial intelligence, and it's called particle swarm optimization, PSO. Now, we have a number of agents or bees exploring the search space. Those are very simple ones. In fact, they can move or fly. They have 2 memory slots each and ability to communicate with others. Now, what they have, well, of course, they have some physical things like ability to move, but also mass, velocity, and that's it. And location, of course. But they can remember the location where they have found the best fitness function, and they can communicate with others so that they know the best fitness function location found by any member of the swarm or herd or any of the agents or bees that are included in this situation. So at the beginning we again have some area. I will draw a 2-dimensional one. And at the beginning we randomly generate several agents, at least the number of the dimensions of that search space plus 1. So we have those agents that are randomly moving. So for each of them we have a vector of velocity, and of course the agent has xi, which is the location, and vi, which is the velocity at the moment. And it remembers its best so far traveled place, and it can ask others to give them theirs best found places so that it knows the best ever found place in the search space. And now, from the initial moment, all of them move with some velocities. Of course, the velocities are random, so they are different for each of those agents. Now, each agent will adjust its future velocity according to several factors. So first, new velocity of an agent would be given by, well, first there is some inertia, so let's call it mass of the agent that prevents him from completely changing the velocity at a moment. So this v stands for the current velocity, v new stands for the next velocity. So there is a matter of inertia. Then the agent somehow tends to return to the position where his best experience has been achieved. That is, to the position he remembers he traveled through a place with excellent fitness function, his best. So to point to the place where the best solution has been found, we subtract current position and the optimum found position. So the next would be the optimum local, his own optimum, minus current position. So this is a vector that points to the optimum, and that he would add with some weight. So let's say A. So he travels with some inertia and a little bit bends back to the direction where he found the optimum. So if only those two elements would be present, he would travel and bend a little bit to the place of the optimum. After some time, this agent would again return to the place where he has had experienced the best fitness function. But he also communicates to other agents, other bees, and so he also tries somehow to bend his trajectory to the place with best ever found fitness function, which I mean now best ever found by any of the members of the swarm. So there is an element with some weight B where he tries to get to total optimum, not this is local optimum, this is total optimum minus his location. So this bends his trajectory towards the global optimum so far found. And there is some randomness which improves detection of a global optimum. So with some weight which is C, this trajectory bends randomly. So given the weights A, B and C, the next velocity of that agent, of that single B, would be adjusted according to what has been found in history by this agent and other agents, and a little bit randomly. Now we have the velocity, we can update the position. New position of that agent would be the current position plus some delta t, some small time, times velocity, which is the new velocity found here. So we will move the agent a little bit. The agent gets to a new location and he examines the fitness function. In the case this position is not very good, that's the end for this step. But if he finds a place with a better fitness function than was his so far found optimum, he updates the location of this optimum in his memory. And he broadcasts this value to other agents, so that in the case that he has in this moment found the global optimum, all the agents would know that and bend their trajectories into that direction. And now this runs and runs till most of the agents converge to a small cloud around an optimum, and then the optimum is found. Now there are a few points that should be addressed. First, what I have drawn here more or less means that the agent will go and somehow collide with the border, with the maximum possible value of the vertical variable. And there are at least three possible ways how to handle that. First, if an agent is on a collision track to the border, well, the first possibility is that we only set the normal component of his velocity to 0. So in that case, he would move along the border for the rest of his movement in this time step. As the optimum so far found must lie inside, he would then bend and go inside. The second possibility is more brutal to the agent. Let's apply Snell's law so that he just reflects from the surface. We have fortunately a computer models so that the change in velocity, which would be brutal in this case, is not important. The third possibility is that we'll let the agent go out, but we stop evaluating the fitness function. So he travels outside, and because he tends to get back to the local optimum, his own optimum, and to the global optimum, his trajectory would bend, and eventually he would again get into the search space, and then the ability to evaluate fitness function would be restored, and the agent would travel somehow exploring the space and getting better and better estimates for the optimum. So this is quite popular method today. It's called particle swarm optimization, and it's used in many scientific papers, so that I wanted to give you the main ideas of that. Your questions, please. Well, okay, if there are no questions, I have a question now. I would like to give you one thing that, in my opinion, is important for an engineer to understand, or would be important in future. But I will not be able to do that in 10 minutes, which is the remaining time of this lecture. We had to start a little bit later. I waited for more students to show. Is there anybody who has to leave exactly at 11:15? May I make this lecture say 10 minutes longer? If that, I have seen a hand, but I may. Okay, so I will try to do it as fast as possible, but I will run out of time. So now, please, forget most of the things we have been telling about optimization since the very beginning. I would like to tell you something about optimization where you have more criteria at the same time. You remember at the beginning I told we construct an error function when we have one real number that evaluates the solution. In fact, in the case we are not able to meet all design goals at that moment, we make a trade-off at that moment. I say, well, okay, price is not important, or mass is not important, but it should do this. So we made, at the beginning of the process, the selection, the trade-off. Then we express this in construction of the error function, and then we made optimization and found a solution. What if we make a more complex process that lets us to make this trade-off only at the end? Because at the end we would have the information what we sacrifice for what. But in this case, we have to accept that there are more criteria, and the situation is a little bit more complex. So what I'm talking about, we have a function of some variables. I will call this, for example, x1 and x2. But we have an advanced optimization method. We will only note that this is the situation. We have several criterions for that, what we call goals. So we have, for example, goal 1 and goal 2. And this is an important situation which has been investigated by a mathematician and economist, Vilfredo Pareto. Pareto is mostly known by a Pareto principle, which says that, for example, 80% of profit from your work comes from 20% of your time devoted to the work. This is mostly cited, but the truth is that Pareto has never told that. What he has been really investigating was the problem, how to distribute sources to achieve maximum profit for all. Now, this is the basic question of the economy. But let's say, for example, that we have a classroom. I wish I can teach in a classroom again. But let's say we are in a classroom. So we are 9 people at the moment. We are 9 people at the moment, and suddenly somebody knocks the door and brings inside a big bag of $100 banknotes. It's several millions inside. And now we somehow can distribute those banknotes between us. Now, Pareto says, well, there is a number of possible distributions. We would call them fair or unfair, we would like them or not. But we have first to distinguish. For example, we can start a war between us, make coalitions, fight, and destroy some of those banknotes when trying to steal all of them for us. So Pareto says, well, there is a special kind of solutions, which we will call Pareto optimal. And now this is a definition. A solution is Pareto optimal if and only if improving one of the goals would necessarily mean to decrease at least one other goal. So you can't improve anything unless you decrease the fitness of other variables. For example, if you have one big pack of dollars, we can distribute them to us, and if you want more, you have to take some dollars from another person there. So this is a Pareto optimal solution. Which will not be a Pareto optimal would be if we throw part of that notes out of the window, because then we could have more inside for one of the people inside without decreasing the number of dollars going to others. So this is a Pareto optimum. Societies are operating somewhere around a Pareto optimum, which could be quite a different one, let's say in Europe and in Africa. We have countries where the, let's say, disbalance between the greatest incomes of individuals and lowest incomes of individuals are very huge or very small. All of those solutions could be Pareto optimal. So we have defined what a Pareto optimal solution is, and we can note that there is a huge number of Pareto optimal solutions. All of them are Pareto optimal. Now, let us define another important thing. Let's say that we have one goal which increases this way and the other goal that increases this way. So for example, if we have this solution, it has this value of G1 and this value of G2. Now I can have another solution, for example this one. Now this is not a very good solution because it has less profit in G1 and less profit in G2. So there is no real need for accepting this solution because it's worse in any manner. We will call that this solution is dominated by this solution. In fact, anything in this field is dominated by this solution. If we have another solution like this, that's a different story because this solution, well, it does not provide as much G1 as this solution, but it provides more G2. So this solution is not dominant over this, neither this is dominant over this one. They have at least one advantage against the other solution, each of them. Now, if we would have